Hello and welcome to the new session of our symmetry and group theory in chemistry. And this time, we're splitting of the terms of an ion under weak interactions is the topic of our discussion. I'm your instructor, Saurabh. The splitting of d orbitals in an octahedral environment, it is customary to see a character table of point group OH. The OH point group has the various symmetry species that have been displayed, large number of symmetry officers that are at your pursual, and their basis factors also represented on extreme left of the character table. We shall see how the various terms actually splits under an octahedral environment in such cases. In earlier videos, we have seen that the five-dimensional matrix can be splitted into a set of D functions. Thus, we have obtained certain reducible representations which ultimately splitted into Eg and T to the set of orbitals for the case of D orbitals. However, if we wish to try the same, that is all for those functions for different values of L, there are possibilities of 2L plus 1 fold set of functions. If we talk about L is equal to 0, we are talking about S level. If we are talking about L is equal to 1, it implies that we are talking about a P. For 2 is about D, for 3 is about F, and so on. So we shall see that how these matrices split when we consider the basis for different L values. We have a generalized formula. We have a generalized matrix that we have seen that by a certain degree of rotation, how a n by n order matrix could have been taken as a basis. For all values of L, we'll have the diagonal values of E, Li alpha, E, L minus 1, I alpha, to the extent it goes to minus L minus 1, I alpha, and minus Li alpha. For example, had it been 2, it would be e to the power 2i alpha, e to the power 1i alpha, e to the power 0, e to the power minus 2i alpha, minus I alpha, and it would have been e to the power minus 2i alpha. So that was a very peculiar case for d orbitals. Now we are talking about a very generalized case of matrix to obtain the characters, or rather characters of reducible representation for various values of L. So we have seen that this also forms a geometric progression series, and solution is in general comes through the chi alpha is equal to sine L plus half alpha divided by sine alpha by 2 if alpha is not 0. Of course, alpha is the angle through which a d orbital or any orbital under the value of L is moved or is rotated. When you're talking about splitting of S terms, and since the S orbital has a spherical symmetry with no theta and phi dependence terms, the representation based on S orbital will include 1 as the character in all the rotational operations. Hence, it goes without saying that the term S belongs to A1G representation. You can refer to the character table, or without even referring it, we'll see that all the values, first two values are plus 1. Therefore, it is the A1G type of representation. When we are talking about splitting of p terms, now for p orbital L is equal to 1, and if we use the same expression, that is rotation by certain angle, would ultimately give the value sine L plus alpha divided by sine alpha by 2, and because L is 1, that ultimately leads to 3 alpha by 2 and sine alpha by 2. For various rotational operations, this formula be used in a straightforward manner. For instance, for C2 rotation where alpha is 180 degree, the value comes out to be minus 1. For C3 rotation where alpha is 120 degree, the value is straightforward 0. For C4 rotation, the degree is 90, and the value of character for C4 rotation is straightforward plus 1. So we have the reducible representations for which p orbitals form the basis that actually we have seen now for the rotational subgroup are eventually 3, 1, -1, 0, and -1. The first value 3 is we are using it because there are 3 degenerate p orbitals. We are talking about p orbital, and rest are the rotational operations for which we are making a basis for a subgroup O of a major group OH. From the character table of the group O, we find that the above representations correspond to irreducible representations, and hence the term P of D2 configuration belongs to T1G representation under the octahedral environment. So what we have to do is we have to simply see that 3, 1, -1, 0, 1, if it is there somewhere in the irreducible representation, we need not go for the standard reduction formula and all that. Even if we will do so, it will ultimately come into T1 species because they are even to the inversion, and therefore we'll say that this configuration would straightforward belong to the T1G representation under the octahedral environment. Let's take some different case. We have discussed earlier about the rotational group of OH. Here what we are saying is 3, 0, -1, 1 and -1 are actually coming from T1. So we'll just say that it is a T1G that is a basis for the p orbital of the same. Your character were 3, 0, -1, 1, -1. Just inspect it here. 3, 0, -1, 1 and -1. These reducible, they are not reducible actually, they are obtained by taking basis vectors. So therefore it is T1, they are the characters of T1, and hence our answer is T1G. When we are talking about D term, we have evaluated in a very early video, the very first video in that regard, and we have seen that it ultimately splits into two sets of orbitals that are EG and T2G. So the next case is before us splitting of F terms. Now when we assume that if L is equal to 3, the characters of rotational are given by L plus half, that's 3 plus half, that is 7 by 2 alpha, and similarly sine alpha by 2. Once we are done with this, what we need to have, put the various values of alpha, that is 180 degree and 120 degree, also 90 degree for C2, C3 and C4 rotation, that ultimately yields the value of -1, 1 and -1 respectively. We are supposed to use these values in the same character table, that is the rotational subgroup of OH point group. And we have the character of 7, 1, -1, -1 and -1. Now 7, 1, 7 is there because for F there are 7 orbitals. That is for the L value would assume from -3, -2, -1, 0, +1, +2, +3. There are such 7 orientations possible, and for the characters of different degrees of rotation, the values that we have discovered are 1, -1, -1 and -1 respectively. And our job is to now see if it can be decomposed into the basis vectors. And if we do so, what we get is A2 and T1 and T2 using the standard reduction formula. They are all to inversions. So now our conclusion is A2U, T1U and T2U must be the same. However, the same idea cannot be used because we are talking about an octahedral splitting, and therefore the term F under octahedral split would be equivalent to A2G, T1G and T2G. And this is our answer for splitting of F term. When you talk about G terms, for G is equal to L is equal to 4, and it is going to assume -4 to +4 including 0 will have something like sine 9 alpha by 2 divided by sine alpha by 2. And once we are having this expression, what we need to do is again put the various values of alpha including 180 degree, 120 degree and of course 90 degree for C2, C3 and C4 rotations, that actually yields the values of 1, 0 and 1 respectively. And in such a case, if we consider again the O subgroup, that is the rotational subgroup of OH point group, we have for the identity, because there are 9 such possibilities from ranging from -4 to +4, we have all these values that are there, and of course they are not irreducible values, but they can be reduced by using some means that we call as the standard reduction formula. Once you go for standard reduction formula and you decompose the values, what we have seen that they are actually belonging to A1E, T1 and T2 kind of species. And because G orbital is symmetric with respect to I inversion, so our corresponding terms are A1G, EG, T1G and T2G respectively. So it's the idea. So it's 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 3 that is 8. So 3 to the 6 and 7, 8 and 1, 9. There are altogether 9 configurations that we have seen for identity as well. Thus, we are able to split the various terms under the octahedral environment. And now the next point is assigning the spin multiplicity. The chemical environment does not interact directly with the electron spins, and the states splitted from a particular term have the same spin multiplicity as that of involved terms. So whatever is the term, whatever is the multiplicity of the term, that will be the multiplicity of the microstate that we are talking about. And therefore, we have discovered something like this. If we start from G, we are supposed to have 9 configurations that we have discovered that there are 1 A1G, 1 EG, 1 T1G and 1 T2G. Because it is the term 1, multiplicity is 1, they by default all of them are 1 and there are 9 microstates that have been displayed. When you talk about 3F kind of system, we have seen that it is 3A2G, 3T1G and 3T2G. And in fact, if we see that because in the term F, the multiplicity is 3, all the terms must be triple 8 as well. So for 3A2G, that means you have 3 plus 3T1G, that was 9, 3T2G, again 9. So we have 9 and 9 coming twice, the integers are 18 and 3, that is 21. So 21 microstates are possible for the 3F term. For 1D, because the number of configurations are 5, and we have seen that d orbital splits into EG and T2G sets, and we have 1G because the multiplicity for D is 1 here, so the states would also have, the terms would have the same multiplicity 1 and 1, and so this is 2 plus 3, that is going to give 5 number of states this way. Similarly, in case of p orbital, there is 9 number of configurations. We have seen that it belongs to only T1G kind of system, and because it's a triplet in the original term, it is also being a triplet tree. So you have 3 T1G, and for 3 into 3, there are 9 configurations or microstates as possible. For a spherical symmetrical species like 1S, there is only one possibility, there is 1 A1G, and the number of states is 1. So this is how the correlation between the terms and the corresponding states for a D2 system comes into the way. Now, why we are talking about D2 system? Because earlier we only talked about the one electron system. Now we are heading towards 2 electron system where the electrons may have either a triplet or a singlet state. That is, both electrons are paired or both are unpaired, and thus it gives rise to many of the microstates that are possible. And later on we are going to construct the correlation diagram from a very weak to a very strong interaction in an octahedral field. Thanks for watching,